Okay. What I've seen, at first glance without looking at the details, looks okay. I can't tell better than okay until I look at the details, so it might look pretty good. Um, First of all, the derivatives are really simple. I'm going to have -2 sine t I plus 3 cosine t j. Let's just plain old k. All right. I didn't ask you to sketch this. Anybody have an idea what this curve looks like? Can you just show me with your fingers what it might look like? Flashing?
Yeah, it is.
Well, what's happening in the XY planes? You got the ellipse. Okay. Is cosine ti plus sine tj is just a unit circle, isn't it? And that's something you ought to know as well as to know the back of your hand. Okay. If you exaggerate the ellipse in the x direction and the y direction, the unit circle, I mean, exaggerate it in the x direction, it's going to go a little further in the x direction. Exaggerate it in the y direction, it's going to go further in the y direction. Exaggerate it more in the y direction than in the x direction, you're going to have an ellipse. It's tall and narrow. Not all that narrow, but you get the idea. And you really have to understand that. And you can sketch that ellipse if you go back to what I suggested you do. You got 2 units here and 3 units here. Now, this is a really bad ellipse because my 3 is about the same size as my 2. If my 3 was right, it would be exaggerated, right? Actually be more like still not great. If I was careful with my 2 and my 3, I'd have a good picture of the ellipse. And we're also going around it in the counterclockwise direction. There's an orientation. Okay. So if you haven't drawn that picture, nobody drew that picture. Okay. So one thing I'm not seeing on your homework is pictures. Okay. Maybe I'll see more pictures when I look at your chapter 3 homework, which is due today. So I'll start looking at it tonight. Okay. You know, most of the homework looks okay. But not seeing any pictures tells me that you're not visualizing what it is you're calculating. You're just doing a bunch of formulas. You're not going to learn much by doing a bunch of formulas except how to manipulate the formulas. Of course, that's significant because formulas aren't that easy. So, but if you don't have the picture, you're not understanding how it relates to the real world. And, you know, y'all are going to be engineers. I hope you learn to relate to the real world. Draw the dang pictures, okay? As best you can. And these vectors, you know, indicate them on a picture. So you reinforce what you're doing, so you don't just have to memorize a bunch of formulas you're going to forget right after the test. Most engineering, most upper level STEM stuff is written in the language of multivariable calculus and differential equations. Okay? If you don't know multivariable calculus and don't know how to visualize these things, you're going to be at a big disadvantage. And if you do know them, you're going to be at a big advantage. Okay, so anyhow, there's your R prime. So what's happening to this thing? Is it speeding up or is it slowing down or is it remaining a constant velocity, or does it velocity maybe fluctuate up and down a little bit? Well, t is basically your angle here, and you got to be moving faster here than you got to be moving here, because you're moving upward along an ellipse that's elongated in this direction. If you take, let me just exaggerate it. Okay, take equal angles. That's supposed to divide first quadrant into equal angles. It didn't do quite well as they could have. It's like this, like this, like this, like this, and like this. Between here and here, you got to move further than between here and here. I didn't draw that real well, so you might want to draw that out and try to really make the angles equal so you can visualize it. Okay. But if you move 30 degrees from here to here, you're going to move further than if you move 30 degrees from here to here. There's more curve to cover. So anyhow, then our double prime of t is -2 cosine t I minus 3 sine tj, and k is constant, has no derivative. So the acceleration of this thing is always in a plane parallel to the xy plane. Now, the other thing that's happening is you're adding tk. That means if I draw this thing in 3 dimensions, okay, well, I've got my ellipse down here. You know, maybe the ellipse comes out to here and out to here, here and here. And I'll draw just a little dotted line for the ellipse. Now, it doesn't follow this path, but its path is always directly above this ellipse. But as soon as it starts moving, it's going to move upward because of the tk, right? So that by the time t reaches 2 pi, you're going to have gone from this point up to a point 2 pi units higher. Has length 2 pi. It's written really small, so you can't see it. But that means if I go here, I go a quarter of that distance up. Here I go half that distance up. Here I go 3/4 of that distance up. And my curve is going to do this sort of thing. And then it's going to keep on doing it. And I've got it narrower and stuff. I should have come out further, and I should have drawn more guidelines and so forth. But you get the idea. You're spiraling upward. It's not a helix because it's elliptical. It's kind of like an elliptical helix, though. Okay. And now you can see what the velocities are going to look like. The velocity this point is going to be tangent to the circle, but it's also going to be somewhat upward. So I need a bigger picture to really depict that. But that's what you're dealing with, okay? You can imagine an amusement park ride, you know, it takes you up a helix, goes faster and faster until you go spinning off. Okay. So these things have meaning. This R double prime is your acceleration. Okay? You have 0 upward acceleration because you're moving upward at constant speed. Okay? So your acceleration is purely in a plane parallel to the XY plane. It's not in the XY plane, but it's just got an I component and a J component. Okay. But you're speeding up and slowing down in the I and J directions. Okay. You know, when you've got, well, let's see what we've got. Okay. So unit tangent. And everybody's got this, I think. This is your R prime over the magnitude of R prime, which is -2 sine T I plus 3 cosine T J plus K. And then you divide by the magnitude, which is going to be the square root of 4 sine squared T plus 9 cosine squared T plus 1. And you could say that's going to be then 4 cosine squared T plus 5 under the radical, because 4 of the the 4 sine squares and 4 of the 9 cosine squares add up to 4, right? Sine squared plus cosine squared is the same thing as 1. Pythagorean identity. Something you should dream about in your sleep. You've used it so often. Okay? Maybe even dream about it when you're awake. Okay? Now, there we have it. That's your unit tangent vector. It looks a little complicated. It's a little hard to visualize, but not that hard. And that's going to be tangent to the curve at every point. There's a lot more I could say about the relative velocities and stuff. But now, what about this A parallel and A perpendicular, normal and binormal? Not sure you see it in section 2. I didn't look closely enough, and I should have. Talked about these pretty thoroughly in the last class, so I'm not going to talk about them again today. You're going to encounter them in some of the homework, if you haven't already. I didn't see a lot of this, but everybody got up to here. And I didn't look that closely to see how far we might have gone beyond that. So it's not too bad. Okay. One thing about your normal vector. Okay. Your normal vector is going to be perpendicular to the unit tangent vector, right? The unit tangent vector doesn't change its magnitude. The derivative of a vector that doesn't change its magnitude is perpendicular to it. Has to be. So this is the first thing you might not have seen. I don't think I've talked about it. I don't think it's in sections that you've done. T of t has a constant magnitude. So if I have T of t t plus delta t, then this little vector here is the change from here to here, from this vector to this vector. Okay? What kind of a triangle does this make? Talk about this for a second. Okay. Now, if you had my physics class, I told you a long time ago to learn why acceleration is v squared over r. It's because of isosceles triangles, because of exactly what I'm telling you now. Okay? This side equal to this side, because these are unit vectors, which means if these angles up here are equal, right? Now, what do the three angles of the triangle add up to? Well, 180 degrees. What happens as delta t approaches zero? Small angle approaches zero, so the equal angles approach 90 degrees. And squeeze it in. You know what the definition of a derivative is. It's a limit as t, delta t goes to zero of big T of t plus delta t minus big T of little t over delta t, right? That's a derivative. It's a definition of a derivative. You better understand the definition of a derivative because chapter 4 is coming up before you know it. And you got to do partial derivatives. You're going to have to manipulate these things, okay? So you want to be sure you kind of review this and look at some problems you've had in previous courses. Perpendicular to t. Normal vector is just the derivative of the unit tangent vector corrected for the magnitude of the derivative. Now, I showed you last time how you can use the acceleration vector and take the parallel component of the acceleration vector, just dot it with the unit tangent vector, which you know how to calculate, because everybody did, okay? And then subtract that from the acceleration vector, and you get the normal component of the acceleration, the perpendicular component. When you see problems like that, don't just follow the formula and think that you've understood it. Draw the picture and reinforce what it is you're doing, okay? Best advice. Again, future, most likely as you're partnering with AI. AI can do the equations. AI can't think of the pictures. Yeah, maybe never. Okay, it's a big hurdle for AI. Being the human being in the loop, you need to be able to think of things that AI won't think of. You need to be able to tell AI, hey, Think about this. Now what do you get? The AI said, I get this. What do you think? Okay. You know, AI will say, I'm a lot smarter than you are. You know, you're really stupid, but you still can be a little bit of good to me. So I'm not going to kill you off just yet. All right. Let's hope it doesn't come to that. Think about it. Visualize, understand. Don't just get good at doing what AI can already do. Okay? In other words, don't let AI dumb you down. Let it make you smarter. Okay? Um, of course, I put this stuff into AI, put the transcript, the class into AI, and ask it to do a summary. Anybody looked at those summaries? I'd like you to look at them, tell me if you think they're useful, and if not, how they could be made more useful. Because I can tell AI to do this or that or the other thing with the summary, and it acts like it really understands. It's really good. Okay. Now, I always have to go through the summary, put some stuff in italics that AI just kind of, you know, uh, didn't think it was important to say it or didn't understand it. Okay. And maybe it's just because I garbled my words or something. And then AI is working off of the transcript that YouTube produces. It's not working off of my voice. Okay. It's a pretty good transcript. Those transcripts. But there's a lot of terminology that is a little confusing. Words that I don't articulate properly, and they're obscure words anyway. So, you don't expect miracles, but when I proofread these things, I don't have to say much. It misses a point sometimes, and I'll put a little paragraph in. So you need to look at them because they're going to be useful to you in preparing for a test. I think I want them to be. And if they're useful to you in another way, I can put up a couple of transcripts. I can put up a dozen. I don't want to do that much, but I could put up a dozen transcripts with different emphasis. Okay. All I got to do is tell AI what I need to tell it. So you tell me how you'd like to see something different or in addition or whatever. It's always a good synopsis and it's well structured. Okay. Well, okay, there we have it. There's your unit normal vector. So we're going on this helix, and now we've always got a vector in the direction of motion and a vector in the direction of our acceleration. Okay. Well, if we're in three-dimensional space, it would be good to have three-dimensional, three vectors to carry along with three unit vectors. And of course, we're moving around, so those three unit vectors are, twisting and turning and everything else. Well, I've told you what the third vector is. It's a binormal vector. The unit tangent in the direction crossed with the normal. Okay? In the direction of motion crossed with the normal gives us a three-dimensional coordinate system. It's always changing in space, but it's one that we're kind of attached to, one that we really pretty well understand. Flying around and around through space, we still know straight ahead and we can still feel the centripetal acceleration and we still know which way feels like up, even if it doesn't feel like up. The way we sense is up. If we're sitting straight in our seat, even though things are in the direction our head's pointing. Okay. These three vectors form something really, really useful. Okay. Now, if we're on a curve, there's a circle that's tangent to this curve. It's the circle that goes through this point, and its tangent at this point is the same as the tangent of the curve. And the circle is sized so that it stays with the curve for a little while. So that the circle is a good approximation to the curve for some distance on either side of that point. Okay? So this circle is kissing this curve. It's called the osculating circle. Osculation is kissing. Okay? The kissing circle, osculating circle. The acceleration perpendicular to your motion is equal to v squared over r. If you familiarize yourself with isosceles triangles, you can easily prove this based on middle high school mathematics. Okay? You don't need pre-calculus. You don't even really need trigonometry. You do need to understand geometry of triangles, and geometry is very, very poorly covered in K through 12 curriculum. So you're a little disadvantaged there, but it's worth digging that out and understanding and being able to prove it. It's a simple proof. I thought it was a simple proof when I was 15 years old. Okay. And I'm not that smart. Okay. When I was 15, I was even dumber. Well, maybe not. You know, I've been getting dumber for a long time. So I'm probably back to 12-year-old level, 8-year. I don't know. Okay. So osculating circle. We have this. R is the radius of that circle. Now, I don't have arrows over the V and the A and the R. And let's just distinguish the R so we don't confuse it with the magnitude of our position vector, okay? And even the OSC here for osculating, so we're really sure we know what we're talking about. Now, it's easy to calculate A perpendicular. You already know V, it's the magnet, you know, that helix, we already wrote down the expression for R prime, which is velocity, okay? And I don't want to confuse the issue by writing out formula for A perpendicular. But I've already told you what you need to know to calculate it, okay? You can find A parallel and subtract it from A. Or use other properties. What we want to know is an equation for the osculating circle. A probably parametric equation. So we got to figure out where the center is. So that's implicitly the center. Well, we want to get this vector. This is a vector. on the curve. Center, oscillating circle. Now, if you're moving in space, you don't know if the oscillate, we're just looking at this thing kind of from the perspective of the binomial vector. We're just kind of looking straight at it wherever it is. Okay. If we have a fixed three-dimensional coordinate system within which we want to visualize this, that osculating circle can be in any plane. What's the plane of the osculating circle? What do you need in order to define a plane? Well, a point and a normal vector would be good, right? Make sense? Okay. Binomial B is normal to the plane. And our point R of t builds a point on the plane. So we get the equation of the plane if we want it. Okay. What else can you say about this vector from the point to the center of the osculating circle? It's in the plane of the binomial, and it's perpendicular to the curve, right? It's normal to the curve. So this vector is just, let's say I got to have a notation for this vector. I want to use V. So just be completely unimaginative, we'll call it W. Parallel to V cross A, you're moving in this direction. This is your direction of your acceleration well, your acceleration can be in any direction, but if you're curving, it has perpendicular component, right? And only that perpendicular component contributes to the cross product. I'll just note that it's equal to V cross A perpendicular component of A, and you can think about that. So what really happens is it's parallel to your unit normal. So this vector is the radius of the osculating circle times your normal vector. Does that make sense? Except that the normal vector is in the plane of motion at that time. In the center of osculating circle is in, the whole osculating circle is in that plane. So that the vector from here to the center has to be in that plane. Okay? And it's perpendicular to your motion, so it's parallel to the normal vector. It's perpendicular to your tangent vector. It's in the plane, so it's parallel to the normal vector. Well, that allows us to calculate the coordinates of the center of the osculating circle, right? And we know its radius, and we know what plane it's in. Now I'm going to leave it at that, because I'm probably not going to ask you to actually come up with the equation. I probably put it on a test for extra credit. Okay? Your book does the equation of an osculating circle in a plane, just in the XY plane. Okay? What I'm trying to show you, though, is that this is kind of complicated. It's kind of hard to visualize. Okay? But it's the kind of thing you need to be able to visualize if you're going to be able to really make good use of the content of this course. Okay? That's more important in some fields of engineering than it is in others. But if you can visualize this and follow the calculations and actually calculate the thing, you're doing real well. I'm sorry, we've got a question here. Okay. Again, the question was asked, where's the binomial vector and so forth? Okay. Just to demonstrate, here I am driving my airplane. Okay. Flying along, and I'm banking strongly this way. And I'm going around a curve as I'm banking. Okay. So I'm going around a curve this way. So where's my tangent vector? Straight ahead. Okay. Do I have an acceleration? Yeah, because I'm changing direction. I have a centripetal acceleration for sure, and I might be speeding up or slowing down, so I have an acceleration in the direction of motion. If there's my parallel component of acceleration, there's my perpendicular component of acceleration. My unit tangent is in my direction of motion, just divide the velocity vector by its magnitude, and you get the unit tangent vector. The centripetal acceleration is normal to that by the isosceles triangle thing, which you really need to understand, okay? So that my normal vector is in this direction. Now, there are various ways to calculate the normal vector, but that's where it is conceptually, okay? So where's my binormal vector? Well, this is one unit vector, okay, in my temporary coordinate system, and this is another one. So where's the third one? I want a right-handed coordinate system, so I do the cross product, and my binormal is up there right where my head thinks it's pointing anyway. Okay? Does that make sense? You want to have that picture, and you want to relate that picture to all these calculations and these symbols instead of blindly following formulas. When you see the formula and use it, you want to think about what the formula means. You want to deconstruct it. You want to understand every possible detail, what that formula means, including how to prove it if possible. Now, again, in your first encounter with multivariable calculus, all of that's probably not achievable by most people. Okay. But you want to do as much of it as possible. All right. So it's all I want to say about the osculating circle for purposes of time and other things. I think we've got a question. Okay, response to question, just repeat. Unit tangent vectors here, unit normals here. You do the cross product and the binormal is actually pointing this way. So we're kind of looking from the direction parallel to the binormal. Okay? That makes sense? So it's like we're temporarily in a position perpendicular to the plane of motion. The plane defined by the velocity and the acceleration, the binormal, okay? And that W is in that plane and perpendicular to the unit tangent, so it has to be parallel to the unit normal, which is why I say, okay, well, it's got to just be the radius of the osculating circle, which is really easy to calculate, messy, but y'all know how to calculate that, okay? I mean, what I saw on the quiz tells me that I'm not going to have any trouble, at least writing out the expression, okay? All right. Okay, I want to change our focus a little bit and talk about arc length. Okay, say we got an R of t parameterized by x of t, y of t, and z of t. Okay. I'm just going to talk about the arc length first on an time interval, some interval between t and t plus delta t. Okay. We move from R of t equals x of ti plus y of tj and so forth. To R of t plus delta t. And that's x of t plus delta ti plus y of t plus delta tj plus z of t plus delta t k. Okay. So how far do we move? Starting to write out next step. So I want to write it. That's writing out the right thing. I just writing it down the wrong. Okay, so displacement here is just this minus this, right? You're going to get x of t plus delta t minus x of t times I, y of t plus delta t minus y of t times j, and so forth. Delta t small. T are continuous differentiable functions. Okay. And that just means they don't make, they don't, your path doesn't have corners. It's smooth. Okay. In no jumps. You don't move from here to there in an instant. Okay. That just assures that this is actually models motion in the real world, at least macroscopic motion in the real world. Okay. And the magnitude of delta R I don't want to write that whole thing out. You know, the square of this plus the square of this plus the square of this, right? Okay. Then delta R is very close to this. If you got a small delta t, you're pretty much moving along a straight line. Okay. And say delta S is how far I move along the path. Now, this means I'm like here, and then I'm like here on a path that maybe looks like this. So this would be t gets me there, or t plus delta t gets me there. Okay. If I calculate this Pythagorean theorem thing, that's the straight line distance. I've got a little bit of curvature. Okay. So my actual path distance is real close to the magnitude of delta R, but not quite there. Okay. Well, since x of t plus delta t minus x of t over delta t is your approximate derivative, definition of the derivative, then x of t plus delta t minus x of t is approximately equal to the derivative times delta t. Make sense? You really need to make sense of that. That's whole concept of differential, which typically pretty shaky when people come out of first year calculus. So you really want to think about what that means. So you add up all the squares of x prime delta t and y prime delta t and z prime delta t, right? And of course, that just equals you can factor out a delta t squared, but it's under the radical, so you just get a delta t, right? So making a little jump here, but to get the arc length, you integrate the square root of x prime squared plus y prime squared plus z prime squared with respect to t.
Here. Wait, I'll make the truth.
So there's your arc length integral. S is the distance you travel along the arc. And it's all just Pythagorean theorem in the fact that your difference in your x positions is just equal to the derivative of the x function times the delta t time interval. Now, implicitly, I'm talking about limits as delta t approaches zero and a summation of all these things. Okay? You would sum up all these things and get this. Your book will tell you in very similar notation. Sometimes they'll use like F, G, and H for the X and Y and Z components. Sometimes they'll use X, Y, and Z. Okay? Don't let the notation throw you. The idea is very simple. Just taking the Pythagorean distance between this point and the next. And then letting the distance between those points shrink down to zero and adding them all up. Okay? Okay. I'll post the assignment here in just a little while. One thing I wanted to talk about today is quadric surfaces. You talk about it next time. You really want to be sure you understand conic sections. The picture I gave you, the two pictures I gave you for hyperbolas and ellipses, parabolas are a little easier to understand. Okay? Be able to sketch those things. Because what we're doing is looking at things, surfaces, where if you cut them parallel to any of the coordinate axes, you're going to get a conic section. Actually, we've got a little more time than I thought. I judged from all the noise in the hall, but people were doing something. I'm not going to take the time to do a three-dimensional sketch, but let's look. Does that surface look like? In three-dimensional space. So you take all the X, Y, Z coordinates that satisfy this. What's it look like? Well, lose my ability to do simple arithmetic. That's 4 times as big as this, so this ought to be 1/4 of that. Duh. Okay. And I was trying to divide 8 into 144, and my mind was fluttering about. Okay. What's that? That's an ellipse. This is X, this is Y. You're going to draw an ellipse. And let's put X out here a little further. Semi-major and semi-minor axes are going to look like this, where this distance is a square root of 72. And this distance is a square root of 18, which equals 1/2 the square root of 72, just so you have a ratio. So I say it's twice as long as it is wide. And here's the ellipse. Now, what's it look like in the plane? Z equals 16. Well, if Z equals 16, Z squared is 256. And you get to add that to 144 and you get 400, right? I think. Okay. You get X squared over 200 plus Y squared over 50 equals 1, right? So I could take this and just visualize, okay, we're going to do another XY plane directly above this one, but using these numbers. Okay, well, the square root of 200 is a little over 14, but it's going to be square root of 200, and the square root of 50 is a little over 7. It's compared to the square root of 72, which is 8.5, something like that. Here you have 14. So I can draw a bigger rectangle where this distance is a square root of 200, and this distance here is the square root of 50. And I can draw an ellipse. This ellipse is higher than this one. So as you move upward, the ellipses get bigger, but they maintain the same ratio of sides. 200's 4 times 50, so it's still a 2-to-1 ratio. Okay? So you can visualize this as a set of ellipses, just stacked ellipses. They just keep getting bigger and bigger. Does that make sense?
Yeah.
Now, what's that look like in the XZ plane. Well, you can see, if you remember what you learned about conic sections, that that's hyperbola. How do you graph hyperbola? You're gonna, I'm just in general, I'm not drawing a picture, but your hyperbola might look like this. So how does that come about? And what's it look like when you put it all together? It's a little bit hard to visualize, but you learn to visualize it by looking at what happens in different planes. Planes parallel to the XY plane, planes parallel to the XZ plane or to the YZ plane. And eventually you get a picture. Okay? So that's what we'll talk about. I recommend you read through the section on quadratic surfaces. There are two more sections of chapter 1 we haven't talked about. One of them is three-dimensional coordinate systems, spherical coordinate systems, and cylindrical coordinate systems, as well as rectangular. Don't want to talk about that yet until everybody's had a chance to really get good with polar coordinates. Okay, and some people do polar coordinates wrong as far as the graphs. And we do want to incorporate that, so make sure you load up on that by the week from today. Okay, but at least scan through section, I think it's 1.6 on quadratic surfaces to get a general idea.